AT X. But don't be too concerned. The only thing that you have to remember here, I'm gonna delete it. And the only thing that you have to remember is that multiplication at this point is the multiplication of matrices correspond to composition of functions. And stop here. We're not developing theory of linear function in details. The nice thing is the following. We can write linear systems in a matricial form. So what we are trying to do here is find a way to find this vector x. This vector of the coefficient of the matrix, of the coefficient of this xt, satisfying the system. But for a moment, the idea here is imagine A is a number, and you are writing an identity with number. So what will you do? Oh, in order to find x, you multiply it by a minus 1. That's the idea. But what is the correct question to ask? Okay, my A, we start from A x t equal B. This identity is simply f of x equal b. If this function f is invertible, if f minus 1 exists, f minus 1 from r to m to r to the n, then f minus 1 of f of x is equal to x. And then, which implies that x needs to be equal to f minus 1 of b. So if we can invert a linear function, we would be able to solve the system. Another question would be, if this inverse function exists, is it linear? The answer is positive. It's linear if it exists. The problem is that it doesn't always exist. It will depend to something that we will call next class rank of a matrix. In general, and in the particular case of square matrices, that they are the only one who are invertible, it will depend by a quantity called determinant. The determinant will tell us whether the function can be inverted. We have to introduce some language. What is a sum? Given a matrix, what is a sum matrix? Is any matrix obtained deleting some rows and some columns. So we have some matrices of all orders until getting to single numbers. So, for instance, assume we have this matrix, which is a 4x3 matrix, A. And let's try to list all 3x3 submatrices. And here. So first of all, we can delete, this is a 4x3 matrix. So if we delete a column, we are left with a matrix having only 2 columns. So we're not interested in deleting columns. We have to delete simply rows. So if we start deleting the last row, the surviving matrix is 1 minus 1, 3, minus 1, 2, 6, 0, 3, 9. Oh, here. Then let's try to delete the third row. And we get another matrix. Let's call this A4. I call it A4 because it's the one that I obtaining deleting the 4th row. So A3 here is deleted row. A3 is 1 minus 1, 0 minus 1, 2, 1, 0, 3, 0. And again, we have to delete the second row and we get our A2, which is equal to 1, 3, 0, minus 1, 6, 1, 0, 9, 0. And again,